inspired, but most of the techniques we are going to look at are going to be information retrieval inspired. Okay, now obviously, when you make real systems, you try to incorporate techniques from both of these perspectives. The key thing is to solve the problem, right? Let me actually just stop here because I went through, even though there's not a lot of slides, but I went through some complex information. So let me give you guys a chance to mull over what I just said and ask any questions. So if you have any questions, just so far what we have talked about, please raise your hands. Okay, so Pak Sue, you are here. Can you go ahead and tell me what your question is?
Can you give us some example to this real life example about this text analysis topic?
Oh, we're going to look at many examples. So just
okay.
hold on for a few minutes. Yeah.
Okay. Thanks.
Any other questions? I want to make sure that you understand these perspectives. The fact that we have these, the natural language perspective on text analysis, the information retrieval perspective on text analysis, and what is our real goal in text analysis. So if that is clear, then I think we are all good, and I can move on. And if that is not clear, now is a good time to clarify. Yeah, I don't see any hands raised. So I'm going to assume that this all makes sense, and let me move on. So when we try to analyze a text document, there are two aspects of text we have to be aware of. The most obvious aspect is the meaning of the text or the semantics of the text. And an equally obvious aspect is the syntax of the text, which is the grammatical relationships between words in a text. Okay. Now, if you sort of give it a moment of thought, you probably may come up with this question, which is to say that, look, as computer scientists, from our early computer science classes, we have been taught how we can work with strings. So for example, when we wrote our first program, especially if you wrote it in C, for example, you say, hello world. You may even say it in other programming languages, right? So that's a text output. That's a string output. Then we know how to process strings, how we can compare strings. And since text is just strings, then why is this such a complicated problem? Can we not just simply use all the string processing, the string analysis techniques which exist in computer science and be done with it? So if you want to compare, for example, two sets of text, then we can just compare all the strings in them. And that should tell us if the two texts are similar. So I'm going to just sort of throw it out to the class. Why do you think that's not a solution? So you can just speak aloud, turn your mic on and speak aloud if you want.
Sorry, can you re-say what the solution you're proposing is?
We are not proposing any solutions. We are still talking about the problem, right? The problem is, given two text documents, we want to find out they're similar or not, because that's what we require to address the question, which text document is going to satisfy our information need, right? So the scenario I'm drawing for you guys is to say, okay, so if we want to compare two text documents, why don't we compare all the words in them or all the strings in them? Because we can do that, right? That's very easy to do in computer science. And what I'm saying is that that is not a solution to our problem. So we can't just take two documents and match the first sentence of document 1 with the first sentence of document 2, the second sentence of document 1 with the second sentence of document 2, and so on. And why is that?
Is that because although the words may be different, they could be semantically similar?
Wonderful. So that's indeed, and I'm sure many of you must have sort of realized this, that that, if we just did that, that's obviously not going to work, because you can say the same thing in different ways. Or you can say the same thing using some words which are common, but many words which are not common between two documents, right? So very nice. So the first thing I wanted to achieve in today's class in terms of your learning goals is, I think, very clear, hopefully to all of you. If not, please stop me and ask me, which is that we can't simply solve the text analysis problem by string matching. That's too rigid. That doesn't address our problem. Right? All right, so let me sort of try and build upon the thought Erza enunciated for, I'm sure, many of you guys, to give you some examples. Okay? So these are under this title called semantic challenges at the word level. So when you take any language, you have a number of these situations which may crop up. For example, you may have the problem of synonymy. So you may have one document which says car and a second document which says automobile. Now notice these are very different words. So if you try to text match car and automobile, they will not match. But they imply exactly the same thing. So this is what's called synonymy. Now there are more complex constructs in languages we have to think about. Another one, synonym is something you guys probably are all aware of. The next few may be a little unknown to you, at least in terms of the terminology. So homonymy refers to the situation when you have the same word but very different meanings of the word. So for example, we say bat and ball versus dancing at the ball. So the word ball in the two sentences means very, very different things. Then we have the problem or the challenge of polysemy, which is we have the same word but related or different meanings. So for example, parting one's hair versus parting is such a sweet sorrow. Okay. Then we can have morphological variations. Sometimes they can be highly irregular. So for instance, study and studied, mouse and mice, and so on and so forth. Okay. Especially if you are, if English was not your first language, when you first started to study English, you may have noticed that English is especially, idiosyncratic in terms of morphological variations. Then we may have misspellings or alternate spellings. I grew up in India, and the English we were taught in India was a lot closer to British English than American English, at least when I was young. And when I first came to America, I would start typing, and a lot of the things which I knew I was correctly spelling were, the word processor would say it's the wrong spelling. So for example, color, I would type with a U, C-O-L-O-U-R. And in American English, color is C-O-L-O-R, right? So you have all of these things. But the point is, whether I type C-O-L-O-U-R or C-O-L-O-R, I imply the same concept, right? So this is the challenge of language, that the same informational concept can be expressed even within a single language in many different ways. And then sometimes the same word can have many different meanings, and different words can have the same meaning. So this is why simple string matching just does not work. Okay. So if that makes sense, let's move to the next slide, and I'll go on a few more slides, and then I'll stop and give you a chance to ask some questions. All right, then continuing our list of challenges. We earlier looked at word level issues. Now there are also issues at the sentence or the phrase level. For example, we may express the same information using completely different structures of sentences. The weather is warm, or warm weather. Okay. Then at the phrase level, we have this issue which is called anaphora, which is reference using often a pronoun to something which was said earlier. So for instance, if I say he grabbed the bottle and shook it, well, we all understand we're talking about someone who shook the bottle. But how would a computer know that it refers to the bottle and not something else? And finally, and this is what makes language very rich, we have idioms and metaphors. So for example, the jack of all trades. We do not imply a person whose name is Jack here when we say that, right? So these are some of the many different types of issues which lead to the richness of a language and yet confound, make it so complex that simple, straightforward ways of comparing text by string matching, that is, don't work. Now, outside all of this, there are other issues we have to think about when we think of trying to analyze text so that we can understand what's happening. You know, the most obvious thing as engineers, and you guys may have been taught all of this, is that the first thing you have to think of when you try to design a solution is how will you evaluate your solution? Because unless you have a way of evaluating your solution, you do not know if solution A is better or solution B is better or solution C is better. Right? So the first thing in an engineering education, and if this has not been taught to you, this is not multimedia, this is fundamental basic engineering and science. One of the things you have to understand is before you start anything of thinking about solving a problem, you have to figure out how you are going to assess the quality of your solution. Because unless you have an evaluation measure, you do not know how to distinguish between different solutions. Okay? So in the context of our problem, we need to evaluate the performance of text retrieval, text comparison and retrieval. And the second thing is, we want to be able to index large quantities of text such that words that do not allow us to differentiate between two documents, for example, are eliminated from consideration, and words that allow us to establish the distinction of two documents are preserved, and that similar words can be identified. Okay, so let me go over the second point, because this is a little deep, and as we go forward, we'll see examples and we'll start understanding what all of this means. And if needed, I'm happy to come back and go over these few slides again after the examples so that you get what I'm trying to say. But I want you to be still able to sort of, at least in some abstraction, understand what we are setting ourselves up for. Okay, so the idea is that, let's say we are trying to compare two documents, and there are going to be words in both the documents which have nothing to do in terms of helping us compare the two documents. And these are words we don't want to waste time processing. So we want to completely eliminate those words. Then there are going to be words which are going to be very critical for establishing the meaning of these two documents. And these words are very important and we want to preserve them. We do not want to throw them away, because if we throw them away, we would be losing the meaning of the documents. Okay. Then there are going to be words which are similar. They may not be syntactically the same, but they imply similar things, or they are morphological variations of each other's. Those are the words we want to be able to identify, okay, and so on. So let's look at the first of these two problems. I'm going to go back just for 1 second to the previous slide. So the first problem was how to evaluate the performance of text retrieval, and the second problem was how to index. So let's look at the first problem of how we can evaluate the performance. And this is, guys, very important concept in computer science in general, but especially now in big data. And pretty much all data nowadays is big data. So it's very important you guys understand this concept very carefully. So what we want to do is to evaluate how accurate our method, our algorithm, our software is in terms of retrieving useful documents. Okay, that's the problem. And what I'm going to talk about here are two measures which will help you to do this. And these are very important ideas. So I want full attention here. The first of these measures is called recall. And it is defined as the fraction of relevant documents that have been retrieved, for example, by an algorithm. Okay, so if you want to compute the recall value, it is the ratio of the relevant documents retrieved to the total number of relevant documents. Okay, so look at this diagram just above the definition. So this, I'm going to use my mouse so that you can see the cursor. So let's say that this rectangular yellowish colored box represents the entire document collection. And let's say that we have some query. So for example, we have some query about SFSU. Okay, and in this sort of orangish, reddish, I don't know what color your screens are showing, is the entire set of documents which relates to SFSU. Okay, and this entire document collection, you can think of this as all documents in the world, possibly. Okay, so this is the universe of all documents. Here is a set of documents which relates to SFSU. And now you put in a query. For example, you go to Google and type SFSU, and Google gives you a list of documents, okay, thousands of documents. And this is the set of documents Google has retrieved. Okay. Now, for example, it is obvious that this set of documents which has been retrieved will contain some of the documents which actually deal with SFSU, okay, with the university. So this is the intersection. It is also possible that it will have lots of documents which actually have nothing to do with the university. For example, if someone wrote on their Instagram, "I'm a student in SFSU," well, that's also a document which has SFSU in it. So Google, for example, Google or any other method retrieves that, but that's not what you're interested in. You don't want to know every person who ever was in the history a student of SFSU. You want to know, for example, something particular about what classes are being offered in the computer science department, taught by Professor Singh, for instance, right? So there are lots of things which are not relevant, and there are some things which are relevant. Okay, so this intersection is the relevant documents which have been retrieved for you by the algorithm. So recall is relevant retrieved, which is this section, divided by the total number of relevant documents, which is this red colored section. Okay, so in other words, what recall is saying is how much of the relevant documents has been retrieved by an algorithm. This is the first measure. The second measure is called precision. And precision relates to the fraction of retrieved documents that are relevant. And just like recall, it's also expressed as a percentage. So precision is relevant retrieved by total retrieved. Okay, so I'm going to repeat these ideas in slightly different words so that you can get it, because if you're seeing these concepts for the first time, these look very similar ideas, but they're very different ideas actually. So recall is the fraction of relevant documents that have been retrieved. So this intersection area divided by the area of the red circle. Precision is the fraction of the retrieved documents that are relevant. In other words, this intersection area divided by the blue circle. Okay. So going back to our scenario where you wanted to know something about, say, classes in SFSU, and you did SFSU classes and you got or SFSU and you got a huge number of documents retrieved. So the relevant documents are the ones which actually address your information need, which is what are these classes which are being taught by Professor Singh. And the recall is going to be those documents divided by the total number of documents which may exist in SFSU about classes which have been taught by me or are being taught by me. Similarly, precision is the number of relevant documents which was retrieved by the algorithm divided by the total number of results the algorithm gave you. So for example, if the algorithm gave you 500 results and only 50 actually had the information you were looking for, the precision is going to be 50 divided by 500. And if 50 is the information what you were looking for, the recall, and let's say the total number of relevant documents was 2000, then 50 divided by 2000 is what your recall will be. Okay, so these are two concepts, and what I want to do is I want to go and look at a few other examples which explain these two concepts, and then we can open up the floor for some discussions and question answers. Okay, so here is an example, or alternatively another way of thinking about the same thing. So precision is how many of the results retrieved by the algorithm are correct, and recall is how many of the correct results have been retrieved. So let's look at this particular scenario. So we have the set of relevant documents, which has 50 plus 20, 70 documents in it. And then we have this set of retrieved documents, which have 150 plus 20, 170 documents which were retrieved. Okay? So precision is the number of relevant documents which were retrieved divided by the total number of retrieved documents, which is 20 divided by the total number of retrieved documents, which is 170, which is about 11.76. Recall is the fraction of the relevant documents which had been retrieved. So it's 20 because 20 have been retrieved, and the total number of relevant documents are 50 plus 20, which is 70. So it's 20 divided by 70, which is 28.57%. Okay. So let me stop here and give you guys a few minutes to think about what we have just gone over. And I want you guys to ask me questions. So again, please raise your hands if you have any questions. And you should. No questions?
So I was trying to think of this in terms of like a Google search. So if Google failed to give you a link that you need, that would be poor recall. And then if Google gave you links that were useless to you, that'd be poor precision, right?
That's right.
Okay.
Erza, go ahead.
Yeah, I was just thinking it must be at least a little bit subjective to determine what information is relevant to your query. So I guess I wanted to ask how you would figure that out.
Yeah, so I think that is that's a very good observation indeed. What is relevant is subjective. Sometimes it's not. So for example, if you are looking up the name of a student whose student ID is known to you, then there is no subjectivity there. This is a clear one-to-one mapping of information. But in general, obviously, this is going to be subjective, and therefore, the precision and recall values in general also will be subjective. Right? I mean, you have, I'm sure, we'll just take Google, not because I want to idolize them or I want to beat up on them, simply because they're probably the most popular search engine. I'm not sure if there are lots of people here who use Yahoo or, some of the other search engines which are around, but the same argument would hold true for Yahoo or Bing and so forth. Okay, but I'm sure you would have come across situations where you're looking for some information through Google, and you type it in, and the first few links are not what interests you, right? And if you've never come across that sort of a scenario, you've simply not asked Google hard enough questions. But if you notice what happens when you, for example, design a search engine like Google, so this is directly trying to address the question. You try to come up with methods which on an average will give you very high precision or very high recall. And that's a interesting story in its own right, and I'm going to talk about it. Can you come up with a scenario where you have perfect precision and perfect recall? And we'll get into that momentarily. But before I do that, I just want to make sure that you guys understand the notions of precision and the notions of recall. So again, recall is how much of what was relevant has been retrieved for you. Precision is how much of what has been retrieved is relevant to you. And you can keep on saying this in many different ways, but the formula should help you. So questions or thoughts or observations? Is this that clear? I've been teaching this class for a long time now, and precision recall is sort of the first intellectually challenging concept which you're exposed to in this class. So I just want to make sure that because we are in this virtual setting, I don't get to see you guys. I don't get to sort of literally point fingers and say, well, you tell me what you think, and that we are not losing the opportunity to understand. Because this is something which is very, very critical for the class as well as for modern computer science. So,
excuse me.
Yeah, go ahead. If you can, so let's see. Who is this? Is it M?
Yeah, that's me.
Okay, yeah, all right.
I was wondering if there's any ways to optimize the precision in recall. How would you go about achieving that? How would you go about determining what would be optimal precision, optimal recall for a given search engine, and how would you go about conducting a survey on that?
So first of all, one of the things I want to point out to you, but also to everyone else in the class, this is not just about search engines. This applies to anything. Okay, number one. Number two, if you look at a generic search engine, for example, obviously what you want to do is you want to be as high as possible in terms of precision and as high as possible in terms of recall, right? You want to ultimately provide for each query everything that is relevant and nothing but the relevant, and only the relevant. Okay, so for a search engine, that's very obvious. Okay, now the situation may be a little different. For example, let's say that you are you're applying the same concept in terms of the decision made by a judge in a criminal justice court. Okay, and in this case, the idea is that, well, the judge wants to convict everyone who is truly guilty. So all the guilties should be convicted. That's your recall, and the precision is that you want to make sure that everyone you convict is actually guilty. Right? Now, when a scenario like that happens, for instance, the default is actually to say that, okay, it's possible that I may not be able to convict everyone who is guilty, but I must make sure that an innocent person is not convicted. Right? And that's modern jurisprudence. Right? So you may say that, look, I may have a low recall, but I must have a high precision. Okay. So the big answer to your question, and that's why I'm glad that some of these questions are being asked. I want to point out to all of you guys that, look, this is a very rich set of ideas behind these two measures, and it really depends what domain you are in and how do you optimize for these. Right? So hopefully that that's a sort of an perhaps a more philosophically deeper answer than you might have been expecting. So this is not a technical set of recipes, but that's simply because these notions themselves are very profound. And you'll see, we will deal with quite a few other scenarios where over the duration of this class, where we'll come across these notions. So as we go forward, hopefully your understanding will become also well-rounded as we go. So other questions? And again, if you have a question, there is a button on Zoom which can help you raise your hand. You can use that. If no one is raising their hands, you can just speak out. That's fine. But if there are multiple people, then I can sort of actually look through it. Lauren, yes, please.
So are these numbers that you gave for examples, like precision being 11% and recall being 28%, are those like common numbers, or because those seem pretty low?
Yeah, no, these are just these are just numbers for this particular example. My point here is not to give you characteristic numbers for precision and recall. This is to help you understand what is precision and recall.
Sure. So what are kind of like some kind of, do you know what like average, what tends to be average and the kind of precision and recall for like, I don't know, the most standard algorithms?
Oh, well, first of all, yes, I know. This is what I've been doing all my life. And the second answer is there is no standard average. It really depends on the context. Okay, so after I teach you guys, I teach a class in bioinformatics where one of the things I'm going to teach them today is, given a particular gene, how do you find similar genes? And in that scenario, depending on the context, the precisions can be expected to be above 0.9 or 90% and more. And then there are problems, for example, let's say in epidemiology, where you're trying to figure out, what is the precision for identifying a person who has been exposed to a pathogen, or is misusing substances, for instance. And there the precisions tend to be much, much lower. So if you do 40 or 50%, you are very good. And in the context of some of the gene comparisons, for instance, if you're doing 40 or 50%, I mean, that's absolutely terrible. That's so bad that it was never ever that bad, even when the thing started, right? So it really depends on the domain. Another example is, for instance, if you are looking, for instance, at military technologies, you're firing a missile and you want the missile to hit. So when you are in non-war-like situations, you get very high precisions. In war-like situations, in real wars, you get lower precisions. Right? So it really depends on the particular context. It really depends on what conditions exist when the particular method is put to use, and so on. So there isn't, so you can't just look at a precision or a recall number, let's say of 12% or 50% and say, well, that's bad. Or look at another one of say 89% and say that's good, because maybe in the good domain 89 is very bad and everyone else is doing 99 plus, right? So it really depends. But I think for now, all the questions you guys have asked in various ways, shapes, and forms have been about how do you design, how do you figure out precisions. But what I want to make sure is that you all understand the notion of what is precision and the notion of what is recall. So Lauren, I hope that still nevertheless addresses what you were trying to ask. And just like Em had asked, this is a complex set of measures which really depend on context, is the real answer. Okay, so there are no simplified single numbers I can give you. But what I want to first ensure you understand is how to compute the precision, how to compute the recall, how to understand them. If that is clear, then I'm happy. And the other deeper questions, as we go further in the class, you will know a lot more about. So any questions in terms of the nature of precision, the meaning of precision and recall, how to compute? I see no hands.
Professor?
Yes, please. Who is speaking?
Malcolm.
Okay, go ahead, please, Malcolm. Yeah.
Could you just please repeat again the meaning of precision and recall?
Absolutely.
That's
So
just a quick one. Thank you.
absolutely, yeah. So let's, let me use this example on this slide to actually sort of revisit this concept. Hold on one second. So you have this scenario where you have some question someone has asked, and the method has returned. So this is the retrieved part. The method has returned 170 answers. Okay. And this part, 50 plus 20, 70, is the number of answers which are actually relevant to the question. So the method has returned many irrelevant answers. Okay. Precision is the fraction of what has been returned to you by the method which is relevant. So in this particular case, the relevant are these 20 because that's the intersection. So 20 divided by 170 is precision. Recall is how many of the actual relevant answers were returned to you. So the actual answers which exist somewhere in a library, in SFSU computing systems, inside Google, for example. So the relevant total number of relevant documents were 50 plus 20, 70, and of which 20 were returned. So 20 divided by 70 is the recall, while 20 divided by 170 is the precision. And this example hopefully illustrates the definition which is here, which is precision is how many of the results that have been retrieved are relevant or are correct. So 20 out of 170 are correct. So that's precision, 20 divided by 170. Recall is how many of the correct documents have been retrieved. There were 70 documents which were correct, 20 of them were retrieved. So 20 divided by 70 is your recall. So hopefully that helps. If not, please feel free to follow up and ask me whatever is not clear. Okay, so if all of this is clear.
Oh, I had a quick question.
Yes, please go ahead.
So the 150 is the retrieved documents, right?
No, the retrieved documents is this full circle here, which is 150 plus 20.
150 plus 20, all right.
Right, and the relevant document is also this full circle here, which is 50 plus 20. And the reason I've split it up like that is because 20 is what has been reported to you by your method.
And the 50 is?
I'm sorry?
And what about the 50? So you said 50 plus 20.
50 plus 20 is what is relevant.
Right.
150 plus 20 is what has been retrieved.
Right.
20 are, 20 is what you've got, which are relevant. Okay. So precision is 20 divided by 170. Recall is 20 divided by 70.
Okay, that makes sense.
Makes sense? Okay. And if it doesn't, guys, don't be guys and gals, right? Ladies and gentlemen, brothers and sisters, comrades, whatever, right? Works. Don't be shy. The whole point we are together right now is because you are here to learn and I'm here to teach. So that, you should never be shy if something seems obvious to some of your colleagues, but is not obvious to you. That happens all the time. To everyone, inclusive of myself. So don't be shy. If something is not clear, ask me. Yes.
So for these kinds of measurements, how do you find out in the end whether something is relevant or not? So
yeah, so remember that was the question which was asked, and that depends on the context, right? So in some cases, the answer is very straightforward. So the example I had given was that, look, if I'm looking at the students who are taking my class, right? And I type in an email address at SFSU, or I type in your student ID number, I should be able to get your name exactly. There should be no ambiguity, right? So some of those things are very straightforward. Some are less straightforward, right? So then your measurement of precision or recall becomes subjective. You have to go and ask individual people or look at individual instances to figure out how well your method is doing. And so when you design systems like this, among other things, I mean, you have to do, you have to go and do user studies with a large number of users to figure out how well your method is working. I don't know if you guys have encountered this, but many times you may go to some system. For example, you may try to look up Microsoft Help. I mean, there's some examples I can remember, like Microsoft Help is one. You go to a web page, or sometimes you go to Amazon and type in some question, and they give you an answer, and then say, did this answer address your question, yes or no? So that's one automatic way of polling you to figure out whether their algorithm is actually providing you answers which are relevant. And then, of course, you can do user studies. So, as part of this class, at some point, I'm going to actually go over the anatomy of a very interesting system which was developed initially. It started as a class project by a group of students who took this class many, many years ago. And then it developed into a very significant result in multimedia systems in computer science. And I will go over and I'll show you different types of experiments which were done to figure out precisely issues like the ones we're talking about right now. Other questions? Comments, concerns? We're all good? So I assume, Lauren, do you still have a question, or is it your hand raised from the last time?
Yeah, no, I do have another question.
Okay, go ahead.
I was wondering, for like algorithm design, I assume that like a lot of the question is going to be trade-offs in between precision and recall, as well as speed.
Why do you assume that?
Or not assume that, but like, is that true that a lot of like algorithms would have like a big part of them would be trade-offs in between precision and recall?
So I'm going to use my professor's privilege and hold off answering that question for a couple of slides.
Okay.
And actually, I have a few slides just on that. So we're going to come to that, and hopefully those slides will be fun. Any other questions? Okay, so let's try to, without further ado, move towards satisfying some of the kind of questions Lauren was last asking. Okay, so before I do that, there is one small alternative definition I also want to expose you guys to, so that you know this exists, and I'll tell you why this alternative definition is sometimes used. So remember, we said precision is relevant retrieved by total retrieved, and recall is relevant retrieved by total relevant. Okay. Sometimes you will see a definition which says precision is relevant retrieved plus 1 divided by total retrieved plus 1, and recall is relevant retrieved plus 1 divided by total relevant plus 1. So basically the same idea, but you add a 1 to the numerator and the denominator. Okay. And the reason sometimes people use this second definition is if, for example, either total retrieved or total relevant is 0, and you use the first definition we talked about, then numerically what happens is you get a division by 0, which is undefined, and you run into problems. Okay, so to prevent that sort of a bug crashing your code, what people do is they just add a 1 to the numerator and denominator, so nothing really changes, but they don't get a division by 0. Okay, so just to sort of emphasize this point, so let's take another example, and this will also help us familiarize ourselves more with these two notions. So let's say that a library has 100 documents, and of these 100 documents, 40 are relevant to a given topic. Okay. And let's say that there is a company called Odoo Inc., which has created a system which retrieves, which allows you to query the library for information. So if you query the library using this system on this given topic, it returns you 30 documents. Right? So there are 40 relevant documents to a topic. You did a query on the topic, and Oodle gives you 30 documents back. Now, let's look at a few different cases and just go over the precision recall computations, just so that we are they're really solidified in our mind. So in the first case, none of the documents, 0 out of 30, returned to you by Oodle are relevant. So it did a very bad job. Okay. So in this case, precision, and I'm going to use the second set of formulae. So is relevant retrieved, which is 0, nothing is relevant, plus 1, divided by 30 documents were retrieved by Oodle. So 30 plus 1, which is 3.2%. Okay. Now, the example here actually is meant to also convey a fine point. Now, if you normally would think that if 0 of the documents are relevant, precision should be 0. But because we are using the secondary formula, the second set of formulae, because we've added a 1 in the numerator and denominator, it turns out that there is this 1 in the numerator. So we get a precision value which is non-zero, very low, but nevertheless non-zero. Okay, so this is just something to keep in mind. Recall, in this particular case, well, again, none of the results were actually relevant. So we got 0 relevant results plus 1 divided by the total number of relevant documents, which was 40 plus 1, which is 2.4%. Okay. So again, intuitively, you would think, well, recall is the number of relevant documents which were retrieved by total number of relevant documents. And if none of the documents were relevant, then the recall should also be 0. But because we added a 1 to the numerator and the denominator, the recall becomes non-zero, albeit a very small value. Okay. So let's go to the second case. So of the 30 documents which were retrieved, let's say 10 turn out to be relevant. So precision in this particular case is the number of relevant documents which were retrieved, which is 10 plus 1 divided by 30 plus 1, which is the first row over here, which is 35.4%. Recall is the number of relevant documents which have been given to you, and there were 40 relevant documents, 10 of them have been given to you. So 10 plus 1 divided by 40 plus 1, which is 26.8%. Okay. Now let's look at the third case, and in this case, all the documents which were retrieved were relevant. Okay, so precision is going to be 30 plus 1 divided by 30 plus 1, which is 100%. Recall is going to be 30 plus 1 divided by 40 plus 1, which is 75.6%. Okay, so hopefully, as you will see, that excluding boundary conditions, which is when number of retrieved was 0, excluding boundary conditions, both the definitions, whether you add a plus 1 to the numerator or denominator, or you do not add a 1, capture the performance of your retrieval method in nearly identical manners. Right? And then I have this sort of, a learning sort of advisory point, which is that the key is do not just memorize the formula or formulae, try to understand what these formulae are saying. And if you understand what the notions are, then you don't really actually have to memorize it. You will be able to use it anytime. And I know I say this, I'm not sure how often you guys even memorize things in these days, but these notions are so fundamental in when we deal with information. It's very important that actually you sort of you really memorize it. These are some of the fundamental formulae of computer science. Okay, so I'm assuming the examples did not raise any issues. If there are, please ask me.
Someone in the chat asked if one formula is preferred over the other.
Okay, thank you for reading it out. So no, it isn't. It just is a question of whether you expect you may have a scenario where you could have a division by 0. So if if you're just doing it for the general case, maybe just use the second formula. But in particular, if you use the first formula, you're not wrong, as long as you don't run into that boundary values situation. And thank you for reading the chat out. Any other questions?
Yeah, I have a question.
Right, please.
So why would you add one to the top and bottom instead of just making a special case in the algorithm for a divide by zero?
Perhaps you can tell me. By adding one, do you lose out anything?
Well, it's not 0%. Well, I guess you don't lose anything if you're always adding one.
Right. So that's why if you notice at the bottom of the slide, I have this point, right, which is excluding the boundary conditions. Both of these definitions capture the performance in identical manners. However, if you're saying that, look, could I just, in my code, look for 0? And if that happens, only then I do something, that's fine. But if you do have a division by 0, you still have to do something, right? So you cannot just say that, look, I can't give you a numerical answer. So even if you do check for it, now what you may say is that, look, I'm going to check for it, and if there is a division by 0, then I'm going to add a 1 to the numerator and denominator. Now, the reason that's not a good solution is because what happens is that then all the numbers you report, except the boundary value conditions, will be of a certain character, and the boundary value conditions and numbers will become a little different, right? Because now you've added a 1, right? So you want to apply the same numerical definition throughout. You want to be consistent in your solution.
I see.
So hopefully that sort of addresses what you were trying to ask. Any other questions? All right, let's then move on. So, this is now getting to the domain where there were some questions raised. Are there trade-offs? What should we expect in terms of average precisions and average recalls for systems and so on? And as I was telling you guys that time, obviously, when you design systems like this, your target is to have very high recall. Basically, you want to retrieve all relevant documents, and you want to have very high precision, which means that you do not want to provide any junk documents to your users, right? I mean, you reject all extraneous documents. So if I were to visually try and capture the idea, so let's say that my precision is plotted on the x-axis and my recall is plotted on the y-axis. So one is the maximum precision, one is the maximum recall. What I want is I want my system to be here, which has perfect precision and perfect recall. Okay, I hope that's obvious. Now, what happens in the real world is that this outside trivial domains, this is almost impossible to achieve. It's not almost impossible. I've never seen it achieved. Okay. So typically what happens is that initially, as you start developing a system, and you keep on improving it because you understand the domain better and better as you work with it, your precision improves and your recall improves. So you are moving in this direction. You're moving towards your target area. But beyond a particular point, you often get into a situation where if you try to increase your precision any further, then your recall drops. And if you try to increase your recall any further, then your precision drops. Okay, so beyond a point, and inverse relationship is generally observed between precision and recall. So that's what you run into. Okay, so let me sort of, maybe even using a somewhat humorous example and a humorous context, try to perhaps explain this this odd behavior for you guys. Okay, so let me do this through a quiz, and I'm going to open the floor. I don't need to name people and ask them for answers. I'm going to just open the floor. I'm going to ask you something, and I would just like you guys to just tell me what you think could be the answer to that question, the first thought which comes in your mind. Okay, so assume that you actually have an interview call from Google. Actually, by the way, I made this slides a long time ago when getting an interview call from Google was extraordinarily difficult. They were a very small company and they were exceptionally selective. Getting an interview call from Google is pretty straightforward now. But nevertheless, let's assume that you got an interview call from Google, and the interviewer asks you the following question: can you design a retrieval algorithm that has 100% recall?
I guess technically, yes. You can just return all documents.
Wonderful. Indeed, right? You can return everything. So if you are making a web search engine, doesn't matter what people type in, you return the entire web back to them. Okay, and if you do that, let's convince ourselves that this is indeed the case. If you look at our formula, relevant retrieved, well, if you return the entire web back, obviously whatever answer you were looking for is also in there. It's not very useful. I know it'll just basically take you all your lifetime plus more to go through the web, but nevertheless your answers are there. So relevant retrieved, you have retrieved everything which is relevant, and you get 100% here, and you get 100% here, right? So assume, for example, that there were 20,000 documents which were relevant. Because you returned the entire web, obviously those 20,000 documents have been returned to you, plus trillions of other documents, but that's not the point of recall. It's interested only if the relevant documents were retrieved. So all the 20,000 documents were returned to you, and there were 20,000 documents which were relevant. So you got everything. So you have 100% recall. Similarly, can you design a retrieval algorithm that has 100% precision? And again, I open the floor. You can just speak out the first thought which comes to mind. This time everyone is quiet. I thought you guys will be equally fast.
If you're looking for just one thing and there's only one thing to retrieve.
So the question is, can you design a retrieval algorithm that has 100% precision?
Either you don't retrieve anything.
You don't retrieve anything, or you don't report anything?
Don't report anything.
Don't report anything. And I think that's correct, right? Because if you return any answer and you use the first formula, so relevant retrieve plus 1, total retrieve plus 1, if you say relevant retrieve, because you have not retrieved anything, you haven't reported anything, so this is 0. So 0 plus 1 is 1. Total retrieved is 0. 0 plus 1 is 1. 1 divided by 1 is going to be 100%. By the way, the other formula will not work because you get a division 0 divided by 0, right? So these seem, I hope you sort of, these are meant to be sort of funny, flippant examples from my side. But I'm hopeful that this has surprised at least some of you, right? So you can have a retrieval algorithm that has 100% recall, but to get that, you have to report everything. And you can have a retrieval algorithm that has 100% precision, but to get to that, you have to report nothing, right? And now probably you start to realize why there is this tension between these two measures, because the way to get to perfect recall will, by definition, lead to very bad precision, because you'll put out lots of irrelevant stuff in your retrieval. And the way to get to perfect precision is the other direction, which is you are not retrieving anything at all, right? So beyond a point, this conflicting requirements of high precision and high recall start coming to play. And therefore, you have the problem that, if you try to push precision up, your recall goes down, or if you try to push recall up, your precision goes down. So
Professor?
that's yeah. Just one second. Let me just finish my thought, and then I'll open up the floor. So with that, what I want to do is sort of stop, open the floor for questions and thoughts and comments.
Yeah, so I was just gonna tell to repeat the whole quiz thing again because it's so confusing. Sorry for that.
So you want me to repeat the Google interview problem,
Yeah,
right?
yeah, please, yeah.
So the problem was there were two questions which were asked. One was that, can you design an algorithm which has 100% recall? And the answer to that is yes, you can, by returning everything which is there. So if it's a web search scenario, you can have 100% recall by returning the entire web for any question that is asked. And why? Because if you so for as I said, let's assume that you have a query on the web which you're asking Google, and let's say that there are 20 web pages which are relevant to the query. Okay. Now, if you return the entire web for every query, so it doesn't matter what your query is, it gives you the entire web, and in this particular case, you get your entire web back, and the entire web obviously contains those 20 web pages. So therefore, you have retrieved all the relevant web pages, and you have perfect recall. Similarly, if you do not return anything, and in this case, I'm using the first formula, okay, then precision is relevant retrieved plus 1 divided by total retrieved plus 1. Now, if you just say nothing, zero answer, nothing matches, then obviously you have missed all the relevant documents. So relevant retrieved becomes 0. So 0 plus 1 is 1. And because you did not report anything retrieved, total retrieved is also 0. So 0 plus 1 here. So 1 divided by 1 is 100%. So that's why you have 100% precision by not returning anything. And you can have 100% recall by returning everything. Does that make sense now?
Yeah.
Okay. All right. Other questions? Comments, thoughts?
So I'm always kind of confused with these types of questions because I'm not sure what it says about anything, because both of these are kind of are often not going to be particularly relevant.
So what I would like to say is, in this particular case, I would respectfully disagree. And the questions are there actually for a reason. And the reason, if you take note, is to explain the tension between precision and recall, right? And that's why these questions are a sort of humorous way of actually bringing this tension out. Again, if you want to return everything that is relevant, one way of doing that, it's not the only way, but one way of doing that is to return everything. Because if you return everything, then you will return everything which is relevant. But if you return everything, your precision is going to be very bad, right? Because in addition to all the relevant information that you've returned, you're going to return a huge quantity of irrelevant information, right? Like just as your colleague asked in the previous question. And I said, well, assume that you have a query for which there are 20 documents on the web which meet the query, really meet the query, okay? And no more. And you have a system which returns the entire web back. Of course, this is not something you'll design in real life, but this is to make the point. Because it returns the entire web back, it has obviously returned those 20 documents also, those 20 web pages also. And I'm using the word documents and web pages as synonyms here. Okay, so you have perfect recall, but you have awful precision. Conversely, if you want to get very high precision, you could just not return anything. And numerically, just by using the second formula which I gave you, which is listed first here, in that case, you'll have perfect precision, 1 divided by 1. And it's not very useful because you didn't return anything. Similarly, the straightforward way of getting perfect recall is also not very useful because you're returning everything, right? So what this tells you, and that's the point, what this tells you, so this is not a trick question, this is actually a very profound set of examples. What this tells you is that the characteristics of a solution which will yield perfect recall in a non-trivial setting, right? In a trivial setting is different. In a non-trivial setting, requires you to do things which will ruin your precision. And the characteristics of what you need to get very good precision will ruin your recall. Because to get very good precision, you want to be as stringent as possible in terms of the answers you're providing. That means as few answers as possible. But that, in the limit, will be 0. You are the most stringent. Nothing passed your filter, but that's not very useful. Similarly, to get high recall, you want to be as liberal as possible in letting things go through, because you don't know, maybe that is actually relevant to the question. And indeed, you'll get very high recall because of that. But that's equally useless because you're going to overwhelm your user with so much of junk that your high recall is valueless, right? So high recall requires you to be more accepting. High precision requires you to be more selective. And these are opposing tendencies. And that's why in any non-trivial information retrieval task, beyond a point, this conflict between these two measures starts to come into play. And if you try to push precision up, recall goes down. And if you try to push recall up, precision goes down. Does that make sense to everyone? If not, then you should say so. If you guys are all quiet, then I don't know whether it makes sense or whether it doesn't make sense, or you guys have all just given up and gone and are having your dinner in front of the TV.
How could you say, so I'm just a little confused about the second one, the precision one, because...
So what I want you to do, Lauren, is I want you to drill down and tell me exactly what confusing.
Yeah. What's confusing me is that how could you say that your answer is right if it doesn't work for the second formula? Because... Meaning? Like, it says that the second formula doesn't work, right? Because you have a 0 over 0. Yeah. So your answer, the answer doesn't seem right because it makes one of the formulas not right.
No, that's not why the answer is not right. The second formula, 0 over 0, is undefined, right? Just like anything divided by 0 is undefined. So the point is that these formulae are providing you ways to quantify your precision and recall, right? And the second scenario, which I sort of drew out here, which is you don't return anything, doesn't actually work for the second formula because it leads to a 0 by 0 division. How it does work perfectly for the first formula, because if you don't return anything, you get a 1 divided by 1, which is 100%, right? So the way to think about this is the following. So the formula, and that's why I remember I said in one of the slides, don't try to memorize the formula, understand the notion. The formula, once you write the formula, there are ways you can come up where you'll fool the formula, so to speak. But what you come up with is not going to be a good solution. So obviously, if you don't return anything, you may have 100% precision, but that's not a satisfactory solution to a problem. Just like if you return everything, again, based on the formula, you can have 100% recall, but that's also not a satisfactory solution. So there are two parts maybe you should separate out in your minds.
Yeah, I think I'm getting confused with.
One is that the formula tries to measure precision recall, and in most of the times, it will work just fine, both of them. There are some times where you can fool the formula. So that's one way of thinking, okay? And that's just to keep in mind. That's not the main point of what I was trying to explain, though. The main point of what I was trying to explain is that you can get 100% recall or 100% precision. But in doing so, what you need to do is you need to make your algorithm, you need to optimize your algorithm in a particular manner. And that particular manner runs contrary to the other measure. So remember I said that when you want to have high precision, you want to be more and more selective. And if you want to have high recall, you want to be more and more accepting of the documents, right? So if you're more accepting, obviously things which are not correct will creep in, and they will ruin your precision. But your recall goes better because you are more and more accepting, and in the limit, you accept everything, you have perfect recall, but very poor precision. Similarly, for precision, you want to be more and more selective. So in the limit, you could end up with selecting nothing. You say nothing meets my criteria. And numerically, you can get perfect precision there, but that's also not very helpful. But more importantly, your recall totally goes away. And that's the tension between the two things. So that's why beyond a point, when you increase precision, your recall goes down. And when you increase recall, your precision goes down. Because beyond a point, when you're trying to be more precise, you want to be more selective. And then you may throw out things which actually could have been right. And beyond a point, if you want to have increased recall, you become more accepting of documents or web pages. That means that you could have, by mistake, you may accept web pages which are not relevant, and therefore your precision will go down. Okay. Other questions? Okay, so if there are no other questions, let's do the following. So what I want to do next is I want to talk about basic pre-processing techniques we use for multimedia. And we are sort of at 1 hour 20 minutes into the class, so let's take a break till 5. Let's take a 5-minute break till 5:26, and let's reconverge at 5:26. You guys can go and have a cup of tea or water or whatever you want, and then we'll start in 5 minutes, and we'll start talking about actual pre-processing techniques for text analysis. Okay, so till 5:26.
All I know is keep you coming.
Okay, folks, so let us continue. So what I want to do now is to talk about some of the very basic techniques we use to analyze text. And as we go through these techniques, even though these are relatively basic, simple techniques, you will realize that they give us enormous power in terms of what they're capable of doing. Okay, so let's start with the first of these. Okay, so the first technique which I want all of you guys to know is called a stop list. So given a set of documents, a stop list is simply a list containing words which for that domain are deemed to be irrelevant. Okay, typically stop lists will contain words that occur frequently in all documents. So for example, in the case of English, the stop list may contain words like the, and, for, with, and so on and so forth. Okay. Now, obviously, stop lists can and should be different for different circumstances. So, for example, let's say that we are looking at a list of papers published from the computer science department. Okay. And in such a case, the word computer is probably going to be very common and is going to be there on basically every paper. And it's not very useful because all the papers have this word. So that's a word which could be placed on the stop list if you're looking for computer science papers. On the other hand, however, if you want to distinguish, if you want to separate computer science papers from biology papers, the term computer will be very important because most biology papers will probably not have the term computer in it, right? So the stop list in the former case will have the word computer because it's not very useful. And in the latter case, the stop list will not have the word computer because it probably is very useful. Okay, so you can think of your stop list basically as a filter which leaves only the words you think are going to be important in a document because it has removed the non-important words. Okay, so it's just a list of non-important words. You put it there in the stop list, and when you pass the document through the stop list, you remove those words. The next technique I want to talk about is called stemming. So often what happens is you will notice that words are small syntactic variants of each other. So for example, we may have the word or the words drug, drugs, drugged, and so on, which all share a common stem, the word drug. Or for example, acid, acidic, acidity, which all share the common stem acid. So what we want is we want to get rid of this sort of morphological variations and reduce words to their common stem. And stemming is exactly what allows us to do that. So basically, once you stem words in a document, you highlight the similarity amongst the documents. Okay, so for example, let's say that we have two documents, and these are toy examples, but the point is just to understand what we are talking about. So the first document has the word drug in it, and the second document has the word drugs and drugged in it. So if I just do a direct comparison, there are no matches. Okay, and yet obviously, as you can see, the two documents are drug related, so they're obviously very similar. But if I now do a stemming on this, the first document which has the word drug will be stemmed to itself because that's the root. The second document has two words, drugs and drugged, and both of them will be stemmed to the word drug. And now, if you look at these two documents, you can see that, well, they contain the identical word. Okay? So stemming can be used to establish the syntactic similarity of terms. Now, there are lots of details and complex things about stemming, but luckily, many years ago, actually in the 70s, someone came up with a method which is called the Porter stemming algorithm, and you can look it up on the web. And there are many implementations of this algorithm. So we don't actually now study stemming as a topic anymore. It's so well established. So you just apply the stemming algorithm, and it will stem the words. Okay. So just like stop list, stemming can be thought of as another filtering technique. However, something to remember is that whenever you use a filtering technique, whether it's a stop list or it is stemming, you are removing information from the documents. And when you remove information, there's always a chance that there is going to be an information loss, and you're going to lose something which is valuable. But typically, we take the chance simply because these methods are so useful in reducing the complexity of the problem. So let me stop here and give you guys the chance to ask any questions.
I have a question.
Go ahead, please.
So these filtering methods are done at the document level or at the search level? So in other words, is your search query changed, or is the actual document that you're searching changed?
Oh, good question. A very good question. So what I've just talked about, you apply at the document level. However, there is an entire sort of research community which also works on transforming your search terms so that you can get better results. But this is not that. Other questions? Okay, so if there are no other questions, let's move on. Now, what we're going to talk about next is, it's really actually an astounding technique. It's a magical technique, and I'll build up to it, and you'll see that even though the technique is very simple, it's a very powerful thing. So what we're going to study this under is the context of trying to compute the similarity of documents. Okay, and this philosophy, which we are going to, to which our techniques will belong, are called the term frequency matrix or the bag of word approach. And they're called bag of words because in this philosophy, each document is represented as a collection of terms, and we do not pay any regard to how the terms were ordered in the document. Okay. So phrase level meaning is disregarded, and we just look at the document as a collection of terms. Okay. And the way we represent a document in this approach is through what is called a term frequency matrix. And this is what the term frequency matrix looks like. So the rows of this matrix are documents, and the columns of this matrix are terms. Okay. And at the ijth position, what you have is the frequency of the term in that particular document. Okay. So the ijth number here is the frequency of the jth term in the ith document. So if I is indexing the rows and j is indexing the column, so for example, F22 will say how many terms T2 I have in document D2. F12 will say how many terms T2 I have in document D1, and so on and so forth. Okay, so given a document collection, what I'm going to do is I'm going to build this term frequency matrix where I have all the documents, I have all the terms, and this matrix is a collection of the frequency of the specific terms in a particular document. All right. So if that's not clear, please raise your voice or raise your hand. Let me just pull up the panel? So no hands raised, so I assume that's all clear. So let's now take an example and build such a term frequency matrix. Okay, so let's say that we have these 4 documents. The first document is all the drugged patients. The second document has the terms patient ward. The third document has the phrase computational drug discovery for patients. And the fourth document has the word the phrase computer algorithms. Okay. And let's say our stop list consists of 3 terms, all, the, and for. So basically, we're going to remove these 3 terms from each of the documents. So once we pass document 1 from it, all and the are removed. So we are left with drugged patients. When we pass document 2 from it, there were no terms in the stop list, so nothing changes. In the third document, the term for is removed. So we get computational drug discovery patients. And in the fourth document, again, nothing changes. We get the computer algorithms. And now we are going to stem these documents. So the word drugged will be stemmed to the word drug. Patients will be stemmed to patient. Patient remains unchanged. Ward remains unchanged. Computational gets actually stemmed to compute, even though that's not a real word. So we get compute. Drug remains unchanged. Discovery gets stemmed to discover. Patients get stemmed to patient. Computer gets stemmed to compute. Algorithms get stemmed to algorithm. Okay, so this is what we get after stop listing and stemming. And now we're going to build our term frequency matrix. So we see that the terms we have are drug, patient, ward, compute, discover, and algorithm. And we have these 4 documents. So we can see that the word drug and patient occur in document 1. We can see the terms patient and ward occur in document 2. Compute, drug, discover, and patient occur in document 3. So drug, patient, compute, and discover. And compute and algorithms occur in document 4. So this entire set of documents is now distilled into this matrix. Okay, all clear so far? If not, please just speak up. All right. So let's take a look at this term frequency matrix. Okay, and let's try to see what it is trying to tell us about our document collection. So we look at this, we see that there are 3 documents, document 1, document 2, document 3, which all have the term patient in it. So we can say that, look, document 1, 2, and 3 may contain information about patients. And let's look at these documents. Document 1 says all the drug patients. Document 2 says patient ward. And document 3 says computational drug discovery for patients. So clearly, all of them do indeed contain information about patients. We can also say that, look, document 1 and document 3 have something to do with drugs. Document 1, all the drugged patients. Document 3, computational drug discovery for patients. And indeed, that's true. Then we can do something a little bit more complex. We can say that, look, document 1 and document 2 are on completely different topics than document 4 is. Because, look, document 4 doesn't share any of the terms with document 1 and 2. And document 1 and 2 don't share any terms with document 4. And let's look at that. Document 1 is all the drug patients. Document 2 is patient ward. And document 4 is computer algorithms. So indeed, right, we can look at this matrix and we can make a very complex determination that documents 1 and 2 are very different than document 4. And then similarly, we can say that, look, document 3 and 4 may have something to do with computing. Because document 3 is computational drug discovery, document 4 is computer algorithms, so they obviously have something to do with computing. And again, we found all of this information just by analyzing the nature of this matrix, the content of this matrix. Right? Now, These were very simple. These were toy documents. But I think you guys can see the point. And that by looking at this bag of word approach, where I'm not concerned about the grammar, I'm not concerned about the phrase structure, I'm just looking at the terms which are in a document, I'm stop listing it, I'm stemming it, and I'm building a term frequency matrix. And yet, after all of these simplifications, all of this perhaps even oversimplifications, I come up with a scenario where in this very concise representation, I'm able to use it to do very, relatively complex analysis of the underlying documents I have. Right? So let me stop here. I know that Pedro has raised his hands, and I want to give him, as well as the rest of you guys, a chance to ask any questions. Pedro, go ahead.
I really like this example. I think it was really good. When you have more complex documents, however, how are the words chosen?
The words are, at this point. So I want to sort of, before I help you guys to learn how to jump, I want to make sure you guys learn how to run. And before you learn how to run, I want to make sure you guys know how to walk. So I'm going step by step. So what you're asking partly will be answered later on in the lectures. But at this point, based on what we have learned, all we are doing is saying that we take the documents, we stop list them, we stem them, and we build this frequency matrix. Nothing more. There will be other things we will do later with this matrix. But for now, just this suffices.
Cool, thank you.
Other questions? No other questions. All right. Let's continue to more involved ways of thinking about documents. All right. Now, the example I gave you was obviously a toy example, and part of it was reflected in the fact that, look, these frequencies we saw were 0-1 frequencies. Either a word was present or it was absent. Now, in a real world scenario, you won't have 0-1 frequencies, you will have larger numbers. So a real term frequency matrix may sort of look a bit like this, with much bigger numbers in there. Okay. Now, if you look at this sort of a real world term frequency matrix, and let's, for example, just take document 1 and document 2, we can see that, look, document 1 and document 2 both have large values for term 1, whatever term 1 may be. They also have large values for term 4. They have small values for term 2 and small values for term 3, and no values for term 6, for example. Okay. And therefore, we could say that, look, because they have very large values for term 1 and term 4, small values for term 2 and term 3, no values for term 6, sort of similar values for term 5, perhaps these documents are very similar. Okay. But if I were to do that, I potentially could be making an error. And can you guys tell me what could be a potential problem with this approach? So to help explain the problem, the approach is I'm taking the raw term frequencies, I'm putting them in a term frequency matrix. And yes, we have already seen examples that this matrix can be very powerful. But now the professor has come back to you and said, well, the real world is a little bit more complex. This matrix, just taken the way it is now, can also be problematic. And the professor is now asking you guys to think as to what could that problem be. Lauren, go ahead.
What if the documents are different lengths? So the frequencies might not add up. Like, just if document 1 has like, 1,000 words and document 2 has like 10,000 words, if like the frequency of the words might not like be representative.
Okay, very good, very good. So what Lauren said was, guys, look, we just looked at the word counts. Okay, but what if one of the documents was very small and the other document was very large? And just because it was very large, maybe it had a lot of term 1s and it had a lot of term 4s, even though it really wasn't like document 1. Okay, so the problem with this approach is that document length is not accounted for, right? And that is very easy to take care of. So what we can do is, rather than using raw frequency, what we can do is we can use the normalized frequency of these terms. In other words, divide the frequency count by the total number of words in each document. Okay, so then rather than a raw number like 610, we say, okay, there are 610 cases of T1. What we will have is we will have a fraction of the words in document 1 which are T1, and a fraction of the words in document 1 which are T2. Similarly, we'll have a fraction of the words in document 2 which are T1, and a fraction of words in document 2 which are T2, and so on. And then what we can do is we can compare the relative percentages of these terms in different documents. And then if it turns out that, look, 50% of document 1 was T1 and 49% of document 2 was T1, then we know that, okay, T1 does indeed happen a lot or in similar proportions in these two documents. Right? Make sense for everyone? If not, please just speak out or, ask, raise your hand. Let me check. Lauren, you have a question?
No, sorry, I forgot to take my hand down.
All right. And if someone can just look at the chat channel also. Okay, so I assume that there are no questions in the chat channel on this yet. All right. So one of the problems I'm noticing with Zoom with such a big class is that the chat button gets completely hidden, in layers. So it's possible that I don't see the chat so easily. So what I'm going to do next time is, when I give you guys time to ask questions, I will just request you guys to look up the chat also and just read out any questions which may be there. So let's make sure that we work together to help our colleagues who are unable to raise their hand and are trying to communicate via chat. Okay. Or actually, what I can say is that I think maybe that's the best way to do it for now. In a slightly smaller class, these buttons are much well organized on my desktop, so I can easily get to them. All right, so let's move on. So what now we have is a normalized term frequency matrix. So each row of this term frequency matrix is representing a document, either with the raw data or with the normalized data. And now what I could do is I can use this information to compute the similarity between documents. And why is that important? Because it's important because if I can compute the similarity between documents, I can cluster the documents. So I can group documents which are all very similar, or I can classify new documents in terms of what topic they may belong to based on the distribution of the frequency of terms in those documents and comparing it with other documents for which I know the topics, which may have similar distributions of frequencies, and so on and so forth. Okay. So this requires us to address the question how we can compute the similarity between documents if what we have is a term frequency matrix where each row is a document. Okay. And the idea of computing the similarity is to define some sort of a distance between the documents. And this is the same intuition we have for distances. So If the distance between two documents is small, then the documents are more similar. If the distance is large, then the documents are very different. So you can imagine some sort of a conceptual space where you have 2 points, hold your hands apart, and the 2 points are 2 documents in this space. And if you bring your hands close till the points overlap each other, at that point the distance becomes 0. That means the documents and the points are identical. And if the points are very far from each other, if you move your hands away, then the distances are larger. That means the documents are not very similar. Okay, so that's what we want to do. So we want to define similarity between documents by computing a distance between documents. All right. So hopefully the intuition is very clear. Again, if not, just please speak up. So what I'm going to do next is I'm going to look at a few different ways in which we can compute these distances. And then we'll stop and give ourselves time to ask for clarifications and address any questions. So the first measure of document similarity is a distance which we are very intuitively used to, which is the Euclidean measure of distance, or in this case, the Euclidean measure of document similarity. So basically, if you remember from your school math, if you have 2 points and let's say the coordinates are x1 and x2 and y1 and y2 for these 2 points, the Euclidean distance between them is x2 minus x1 square plus y2 minus y1 square and the square root of that. Okay, and it's the same idea we're going to apply to documents. So if you were to take our term frequency matrix computed in the very first case, so we had these 0, 1 term frequencies. So document 1 now has 1, 2, 3, 4, 5, 6 dimensions. So it's in a 6-dimensional space, so it will have 6 coordinates. And in this case, the coordinates are just what we have in the term frequency table. So 1, 1, and then 4 zeros. Document 2 will have a 0, 2 1s, and then 3 zeros. Document 3 will have a 1, 1, 0, 1, 1, 0, and so on and so forth. And document 4 will have 3 zeros, and then a 1, 0, 1. So these are the coordinates of the documents. And now that I have the coordinates of the documents, I can apply this formula and I can compute the distance between these documents. Okay. So this process where you take the documents, or for that matter, any data item which has different attributes, and think of these attributes as coordinates, is called the vector space representation of information. So in this particular case, what we're talking about is a vector space representation of documents. Right? So in the general case, we will have possibly n terms. So they're going to be n coordinates. And then we have to compute the distance over these n coordinates. So let's take an example. So let's say that we have 3 documents and we have 3 terms. So the first document has 6 instances of T1, 3 instances of T2, and 1 instance of T3. The third document has 5 instances of T1, 3 instances of T2, and 2 instances of T3. So you will think about it and say, okay, well, they seem to have very similar numbers of T1, T2, T3, document 1 and 3, so the distance between them should be small. And let's see if our notion of calculating the distance actually captures this intuition. So we'll just put this in our Euclidean distance formula. So it's the square root of 6 minus 5 square, 3 minus 3 square, and 1 minus 2 square. So 6 minus 5 is 1, so it's the square root of 1 plus 0 plus minus 1 square is 1. So it's the square root of 2 overall, which is 1.4. So this looks like a smallish number. Well, let's see what about distance of D2 and D3. And they are different looking documents. As you can see, T1 is twice and 5 times, T2 is 8 and 3 times, and T3 is none and 2 times. So the distance here is going to be 2 minus 5 square, 8 minus 3 square, and 0 minus 2 square, and the square root of that, which is square root of 38. So 2 minus 5 is 3, so 3 square is 9, 8 minus 3 is 5, 5 square is 24, 0 minus 2 is 2, 2 square is 4. So 24 plus 4 is 28, 28 plus 9 is 37, right? I don't know why I have 38. 25 and 4 is 29. 29 and 9 is 38. Sorry, I was off. 38. So this is all correct. Okay. So 38, and the square root of 38 is 6.16. So you notice, indeed, that the Euclidean distance captures the intuitive notion that documents 1 and 3 are probably quite similar, and documents 2 and 3 are quite different, as this distance shows. Okay. Any questions?
Sorry, this is probably kind of a silly question, but why are we taking the distance instead of just like adding up the sum of the differences?
Can you tell me what you mean when you say add up the sum of the differences?
So instead, for like distance 1 and 3, so the differences are 1, 0, and 1, like the absolute value of the distances. Why don't we just say like the 2 then?
So Lauren, you do realize what you're just saying is another definition of a distance.
Yeah.
That's just not the Euclidean distance, it's a different distance.
Yeah.
You could do that too. Yeah. So that's actually what is called the L1 norm. And this is the L2 norm. So yeah, that's another distance.
Okay.
There are many ways in which distance can be calculated, as you shall see shortly. So to continue the example, here is a different way of computing the distance between documents, not the Euclidean distance. Okay, and this is what is called the cosine distance between documents. And often in document analysis, not always, but often in document analysis, the cosine distance is actually preferred. Okay, so again, we have our term frequency matrix. So I'm just working with the raw numbers. You know, the same idea will go if you obviously normalize and have a normalized term frequency matrix. And what I want to do before I actually show you how to compute the cosine distance is I want to just give you the intuition behind the distance. Okay? So let's say that we have this high dimensional space. In this case, I'm simplifying just by showing a 2-dimensional space. So 2 terms, but normally this could be in 6 terms or 600 terms. And you have your document 1 here, and you have your document 2 here. So this is your document 2 vector, this is your document 1 vector. And the vector is just the set of these zeros and ones. Okay. Now, when I compute the Euclidean distance, what I'm doing is I'm computing this distance between these 2 points. Okay. Another way of thinking about the difference of these 2 points is to think about this angle between these 2 vectors. Now, how will this angle behave if the documents are similar? The angle will become smaller. And if the documents are very different, the angle will become larger. Okay. So instead of measuring the actual distance between the points, I can actually measure the angle between the vectors of these documents. And this is what is called the cosine distance. Okay, so let me actually go ahead and describe the distance, and then we'll stop and give ourselves time to ask questions. Yeah. So I'm sorry, did someone have a question right away?
I had a question from previous slide. Like, how does that change the issue that was arise, like when you had like?
Hold on, which slide are you talking about? This one or this one?
Yeah, the ones where you were using like the frequencies to compute the distance. So like when we were using like 6, 3, 1, like those are frequency, right?
Yes.
How would that change the issue of like not considering word counts?
How would what change? Can you expand on your question?
So like, you know how initially you asked like, oh, why is this a bad idea to just, you know, use the data when it were like 600 and whatnot, right? Because they only care about currently this only cares about how many times this word appears in that document. It doesn't say like say what if document 2 only have 10 characters. I mean, not 10 characters.
Okay, I get your point. So what you're saying is that so let me tell me if this is what you're asking. So what you're saying is that, look, you're right now working with raw frequencies,
right?
But you know, you had just said that, look, by normalizing it, it's better. So why not normalize? Is that what you're asking? Or what,
Right.
what would normalization do? Is that your question?
No, like I'm saying, like right now they're like, so for say like document 1 has 1,000 characters, right? I mean 1,000 words, and then document 2 has 10 words. So that means like 80% of the document 1 is what you're looking for. Therefore, it's more relevant than document 1, right? So, so isn't it better to compute the distance of the frequency rather than the I guess that comes down to what you simplify it to.
Yeah, okay. So just to take your question and to make sure everyone else understands. So let's say the document, so remember, we are not looking whether document 1 has more terms or not. We're trying to compute the similarity between documents, right? So if document 1 has 6 term 1s, but it has 600 words in it, then only 1% of document 1 is term 1. And if document 2 has only 2 term 1s, but it has only 10 words in it, then 20% of document 2 is term 1, right? And these proportions, obviously, if you normalize it, you will get those proportions. The raw score does not give you those proportions. So that we established. We all understand that, okay? Now what we're talking about is how to compute distances between documents. And what I decided to do is I just decided to work with raw scores, simply because it is easier for you to understand the computation. So if I divide 2 by 10, which is 0.2, and 6 by 600, which is going to be 0.01, then these numbers will change and it will be much harder for you to follow. So just so that you guys can follow more easily, I'm using the raw scores. But obviously, in general, you should normalize and use the normalized scores. But regardless of whether you use the normalized score or the raw score, the formula will work identically. Okay?
Thank you, Professor.
Sure. So to continue about the cosine distance. So the Euclidean distance is this distance. The cosine distance is the angle. And if the documents are similar, the angle between them will be smaller. If documents are dissimilar, the angle, pardon me, the angle between them will be larger. All right. However, there's an additional advantage of using the angle rather than this distance. Can you guys just intuitively think of what that advantage could be? The answer is actually on the slide, but I just want to see if you can look at the picture and you can guess what that answer is. Don't read the slide. Just see if you can push yourselves to think. No? No one wants to take a chance? The question is, what is the advantage of using the angle rather than this dotted line, which is the Euclidean distance? Because the angle is smaller if the points are close. Well, if the points are close, the dotted line is also smaller. And the angle is larger if the points are far away, but the dotted line is also larger if the points are far away. So then why use the angle, or what is the benefit of using the angle over the dotted line? Any thoughts? Okay, so let me give you the answer. So this is actually a little bit to do with some of this normalization stuff, which you guys had asked and I was just talking about. So if you think about this, if I just use the raw scores here, right? This could be because I have term 1, let's say 200, and term 2, so this axis, if it's term 2, let's say 800. But what if I have two documents where this vector is not that far? The vector is exactly that, but the point is over here. In other words, we have two documents, one is large, one is small, and they have terms, similar terms in similar proportions. The Euclidean distance will not capture that aspect, but the angle will remain unchanged even if this document over here is, I pull it down and bring it over here, right? So bottom line is that the cosine distance better captures the proportionality of words in a document than the Euclidean distance does. Okay, and that's why in text analysis, they prefer mostly to use the cosine distance. Okay. So let's just move on. You know, what I have in the second half of the slide is just another way of explaining the same thing. So let's move on to the question of how do we compute the cosine distance. So let's say that we have two documents represented by the document vectors, which are rows in our term frequency matrix. So the cosine distance is computed as follows. So let's say that we have a vector x. This is a document which has, these term frequencies. The length of this vector, the length of this document, is given by the square root of some of the squares of each of these terms, each of these numbers. So length of x is square root of x1 square plus x2 square plus so on, all the way to xn square. Okay. Now, let's say that we have a two-dimensional scenario, so only two terms. So let's say that x1, y1 represents the first vector, the first document u, and x2, y2 represents the second document, v. Then the cosine of the angle between u and v is simply the dot product of uv divided by the product of the size of u and the size of v. And the size of u and the size of v is something we just saw in the previous slide. The dot product is simply, sorry, let me go here. So the dot product is simply x1 times x2 plus y1 times y2. And the size of u is square root of x1 square plus y1 square. Size of v is square root of x2 square plus y2 square. So that's what gives us this formula. Okay, so in the general case, if this is our term frequency matrix, and we are looking at n terms, and let's say we are looking at two documents, di and dj, and we want to compute the cosine distance between di and dj, what we do is we just simply multiply fi1 with fj1, fi2 with fj2, and all the way till fin with fjn. And then we divide this numerator by the square root of fi1 square plus fi2 square plus all the way till fin square, multiplied by the square root of fj1 square, fj2 square, all the way to fjn square. So this formula over here. Okay. And that gives us the cosine distance. So let me stop here because, I'm not a big fan of going over formulae without a board to write them in, because it's always harder when just a formula is thrown at you on a slide. So I want to give you guys a little bit of time to look at it. This is very simple. Math has a way of looking daunting, but this is very simple. So take a look at it and ask me whatever is unclear.
So I just wanted to clarify, since, so are you saying that taking the cosine distance or cosine angle between two vectors eliminates the need to normalize them?
Well, let's see. That is a side effect. Yes. But more than that, what the cosine distance allows you to do is to capture the similarity of documents where similar terms occur in similar proportions.
Okay, thank you.
Other questions? Especially what I'm looking for are questions about the mechanics of computing the cosine distance. I want to make sure that you guys actually understand it and are not stymied by it. So take a look at this formula while I go down and see if anyone has their hands raised. Take a look at this formula and just confirm to yourselves mentally that you understand what it is, number one. You can see the mechanics of the formula and that it's not actually very hard at all, even though it may sort of, look, the formula here looks pretty daunting, but it's not. It is very straightforward. As you can just see, you basically just multiply, the dot product, which is the multiplication of these terms, and you divide it by the size of each of these vectors, the product of the size of the vectors, and the size of the vectors is simply the square root of the sum of the squares of the individual elements in each of the vectors. Pedro, yes.
Maybe I missed this, but it seems like the cosine angle could be a bit misleading if you have like a document that's on the same angle but further out, if that makes any sense. So when you're
looking, so the cosine, so I think that's a good question. So what you're really saying is that, look, let's say that we have, I hope you can see my, I'm not in presentation mode, but let's say that the V is right where it is, and the U is further out, or it's further in. Okay. Now, when the U goes further out or further in, the Euclidean distance will change between V and U, but the theta can remain the same, right? So when the U goes further out, essentially what it's saying is that the two documents have the same terms in the same proportion. But the Euclidean distance would have increased, obviously. So for example, imagine if I kept on pulling this U out all the way over here, right, at the edge of my screen share with you guys. And if that's where U is and this is where V is, obviously this is a much larger Euclidean distance than this one over here, right? But the cosine distance will not change because this theta has not changed. Okay. Now, again, in some domains or in many document analysis domains, that's a very desirable property. But it's also quite possible that in some domains, the Euclidean distance actually captures the desirable property. So you really have to, figure out which of these measures is best suited for your particular problem domain. Right? And that's why this is a 600 level class, and this is a graduate class also, paired, right? Because we are now not looking at trivial problems where I can just give you a dictionary of recipes and say, oh, see this problem, here is the answer. No, what we are doing is now we are looking at real problems. So to solve real problems, I'm trying to teach you all the concepts. And then each individual instance of a real problem, if you understand the concepts, you will say, okay, the answer probably is one of these 4 or 5 ideas. Which one depends on the particular context domain. So I have to try these 4 or 5 ideas. I need to have measures to judge how well things are going. And then I can, based on that, I can pick up a particular idea which I find is most supported by the evidence. And then I can go to my boss in the company or wherever I'm working and say, look, here is the evidence. I tried these 4 or 5 different ideas. This is how they differ. And this particular idea seems to work the best in this domain. Right? So that's the bigger picture. The smaller picture, Pedro, for your question really was that, I could change the position of U or V or both without changing the angle between them. And I think that was one of the questions which was asked earlier also, is that, so why the cosine distance? Does it just simply help us deal with the fact that we have to normalize? Well, yes, but the real point is that, look, as long as the ratio of the terms are similar, the cosine distance will capture the similarity, while the Euclidean distance will not. And whether your domain requires you to actually be able to say that, look, if two documents are similar, if they have similar terms in similar proportions, that's up to the domain and up to you to decide.
See,
yeah, go ahead.
So I don't understand why the same result can't be achieved by using the Euclidean distance method on the normalized frequencies.
So as I said, that it would indeed. That is an effect which you will gain if you normalize and use the Euclidean distance. That's not excluded at all.
Well, I guess what I'm saying is if you're using the Euclidean distance method on normalized frequencies versus using the cosine measurement method, would there be any difference?
So what you're saying is that if you're using, let me clarify, if you're using normalized frequencies, okay, and so normalization, I'm assuming in this case, implies that the proportion of the terms is what is being captured, right?
Yes.
And then you are using the cosine distance also on normalized frequencies or on raw frequencies?
In raw frequencies.
Then it would be identical. The point I'm making is a different one. The point what I'm making now is what I was trying to tell Pedro in his answer, is that whether, so again, let me take this thought experiment. So let's take this U and pull it out all the way till here, okay? The angle theta does not change. And cosine distance, if U is here, will be the same for U and V as if U was here. The Euclidean distance, if U is here, would be different, okay? Now, whether your application requires you to have a different distance when U is here, even if the theta is same, or it requires you not to have a different value, that is something you have to figure out. What does the requirement, the semantic requirement of your application suggest? Right? Sometimes you may be in an application setting where you find out that, look, when U is over here, the fact that the Euclidean distance changes actually better captures what is needed in the domain. And then you say, okay, even though in general the cosine distance is desirable in text analysis, for my text analysis problem, actually it's turning out that the Euclidean distance is actually working better. It is more suited to what people think are the right retrievals. So then you use the Euclidean distance. Or, like one of your colleagues was suggesting, use the L1 distance, use the just some of the absolute differences. So which distance works in which setting is something which you have to empirically figure out. That was the part I was talking about last. Okay. So hopefully that addresses it, but think through it some more. If questions remain on this, I'll be happy to take them in the next class. But beyond that, again, I'm repeating myself, but the mechanics of it, mechanics of cosine distance calculation. And I'm repeating myself because my long experience has taught me that it is the mechanics where people often make mistakes. So for I noticed that there is obviously a certain group of you guys who are now interacting, who are asking questions. I'm very happy. But there's also a much bigger group of people who are just very quiet. And especially to those who are very quiet, who have not asked me anything, is it because everything is crystal clear? It's like hot knife through butter, straightforward? Or is it because nothing is clear? And this is, our first real technical lecture. So if nothing is clear, I'm happy to go slow or stop and revisit what is not clear. Or is it because, you're just enjoying the movie? Having chips and enjoying a movie, in which case, you're wasting your money. So I want to make sure that if you are indeed quiet, that's because everything is clear. And if it's any of the other two, then come back and ask all the questions which were not clear. Okay, so everyone is very quiet. The silence of the graveyard. Okay, go ahead.
Just want to ask, what determines the vector length?
The vector length is determined by which terms are present in what numbers, right? So length of this vector is just the square root of the square of the frequencies, the term frequencies.
Oh, right. Okay, thank you. And one more question. What does normalized frequency mean?
Normalized frequency was, when you took the raw number of terms. So let's say that T1 was 10 here, and you divided it by the total size of document 1. So let's say document 1 was 100. So you would divide 10 by 100. And let's say here T1 was 12 and document 2 was 2000 words. So you'll divide 12 by 2000. So you basically divide each of these numbers by the size of the corresponding document. So you get the percentage of the document, of that particular document, which is taken up by a particular term. Make sense?
Yes, thank you.
Okay. Any other questions, guys? Good. So feel free. I like students to ask questions. I think studenthood, you guys are, the point you are in your lives, you should have lots and lots of questions about everything. Science is about asking questions. Engineering is about asking questions. Okay. If after all my extortions, everything is quiet, that means I
guess I got.
Oh, you have a question? All right. Yes, Erza, go ahead.
Okay, so if you're using the Euclidean method if you have the option of using the Euclidean method on your matrix, or using the Euclidean method on your matrix where you've normalized the frequencies,
yes,
and that is the same as the cosine measure method, in what instance would you use the cosine measure method?
No, so there is a fallacy in your question. That is not the same as the cosine, which is what I've been saying many, many times. So numerically, in that particular instance, it will be similar, but the Euclidean distance is measuring the distance in the space, and the cosine distance is measuring the angle. They are not the same.
Yeah,
right? The cosine function takes very different set of values than the Euclidean function takes, right? So to go back to the question you are asking, so when should I use the cosine distance and when should I use the Euclidean distance? Effectively, is what you're saying, I think.
Yes.
And the answer to that is it depends on the domain. You have to look at the domain. You have to see which distance performs more reasonably in terms of what people expect in the domain. So I have, for example, in my research, in different domains, we have had to use different distances. So, a lot of times we have used the cosine distance. Then we have had other domains where we have tried the cosine distance and we have tried the Euclidean distance, and we have found the Euclidean distance to be better. Okay, so this is a very domain-specific answer. And that's exactly what I'm trying to say, is that, look, the fact that normalizing your frequencies will lead in terms of, the similarities, which document is similar, which document is next, and the order of similarities will lead to the same answers for cosine as well as normalized Euclidean, does not mean that cosine and Euclidean are the same, or cosine and normalized Euclidean are the same. They are different measures. This is a side effect, that the rankings will be the same, but the actual values each of these measures provide may be more or less suited based on a particular domain context.
Okay, I can see what you're talking about now.
Okay. And again, some of this is a little, this is a little hard. And I'm here, I'm thinking if I was sitting with you guys as a student. So what is happening is you are actually seeing many of these concepts for the first time in this lecture. Okay. And I've been doing this for decades now. So I have all of these examples which I've seen all of this apply. And you guys are seeing this and you're asking, which are very correct, intuitive questions, right? I mean, so what happens? But what is missing right now in your education is the experience part of it, right? And the experience cannot come with the lecture. The experience is something you have to earn it yourselves, right? So that's why I said that, look, when you work with real world problems, where there is no one single trivial answer, what will happen is that in a class, you will be educated about all the various possibilities, all the various technical ways you can think about the problem. But because every problem is different, I cannot foresee every problem. There are infinite number of potential problems, you may have to deal with, when you try to apply these techniques. But what I can do is I can teach you the way to think and how to go about it and how to measure your performance of your methods, precision and recall. And then when you apply them to your problem, you say, okay, so I knew about Euclidean, I knew about cosine, and there was a colleague of mine who said, well, you could actually add up those frequencies, and the professor said, yes, that's a distance too. It's called the L1 distance. So I could use the L1 distance, and then I have precision and recall, and let me see which of these distances based on my data leads to best precision and recall. And then that's evidentially the best solution to take. Right? So that's how sort of advanced science and engineering works, which slowly, I don't know how many of the 600 classes you guys have taken, or if you're graduate students, how much of this you've been exposed to, but that's part of my mission is, I want to not just throw some formulae at you guys and some cool sounding, or cool examples, but I want you to really train you guys to become strong technical intellectuals. All right, any other questions? So I actually, let me see. We are about 13 minutes from our time. So let me do the following. Let me just finish one more slide. I think, we're going to run out of time today to do anything else, and give you guys some more time to ask questions. And then we will continue on this. So the last slide I want to talk about today are two, first of all, the two questions, and one sort of, be careful note. So the first question, and we'll start at this slide next class, so you can think about this a little bit. The first question is, what is the complexity in terms of how much time, how much memory it will take to apply the kind of techniques we have talked about today in a document similarity determination problem with large number of documents? Okay, what is the complexity of the approaches we have talked about? And the second question is, so if you notice what we have done today is we have said that, look, we have terms in a document, we'll make a term frequency matrix, convert that into a vector space representation, compute Euclidean distances or cosine distances on it, and based on our domain, we'll figure out which of these distances work better. Okay. Now, implicit in this whole idea, and this is something actually I thought someone may ask a question, but no one did, but implicit in this whole idea is another fundamental question, which is, well, did we not treat all terms to be equal? And indeed we did. So after stop listing and after stemming, once we make our term frequency matrix, and once we have our vector space representation, we may have more or less of a term. So the frequency of the term matters, but we have treated all terms to be equal. And the question is, well, is that assumption actually really true? Is it really true that all terms are equal? And our own experience will tell us, well, that's not really true. Right? Oftentimes, some terms are more important than other terms. And how do we figure that out? So in the next lecture, I'm going to show you a technique. Actually, I'm going to show you two techniques where we can address that question completely automatically. So we can automatically figure out which terms are important and which terms are not. So when the domain changes, the context changes, we don't need to know anything about it. Our algorithm will do the job for us. It's almost magical, but that's what we're going to look at next lecture. The first question I still want you to think of, what is the complexity of such an approach? And we'll start with that next time. And the final cautionary note. So, you have projects, I grade projects, I look at how you guys code. And then I've seen this even when I was in the industry, what people were doing. So this is a very silly but common mistake people make. So the term frequency table can be represented in two equivalent ways. The first way is you have documents on the rows and terms in the columns, like we did in the lecture. We can also have terms in the rows and documents in the column, which is just the transpose of the first matrix. Right? And they are equivalent representations. So this is a coding issue I'm talking about, not a conceptual issue. There is no difference between these two. However, in your coding, never intermix these two representations. So don't have a situation where you have documents in the rows and terms in the column, and somewhere later you have another matrix where you have terms in the rows and documents in the column. Or you read you read the matrix and you confuse these two ideas. This happens surprisingly often. I don't know why. Okay, but my bitter experience in life, I'm sharing with you so that you don't have a bitter experience, which is that do not intermix these two representations, even though they are equivalent, but only if used consistently. Okay, so I'm going to stop the technical part of the lecture today. We have about 8 minutes, and then we have to close because I have to go to my next lecture after that. But the 8 minutes we have, I'm happy to take any questions you guys have.
How might, excuse me.
Yeah.
How might all these concepts, so all of these can be extrapolated to any one of the projects? So all of these are foundational for the
any of the
projects?
projects which are relevant to text analysis, you will be using all of these concepts. So what I'm teaching you here is a bottom-up pipeline to do text analysis. And by the time I'm done covering text analysis, yes, you guys won't be experts. There are a lot of things which are complex, which take a couple of years to teach at the graduate level. So I won't be able to cover all of text analysis, but you will know a surprisingly large amount of text analysis at a very solid high level. So other than probably the most recent work which is coming out with deep learning and text analysis, you'll know pretty much everything else. Sanjay, you have a question.
Yeah, I wanted to ask about the stop listing that we came earlier in the slides, like the words like all, for, the, and stuff like that. So do we need to, like, while coding, do we need to like pre-build all of the list to use it in the document for the documents, or is it really related to the documents that we are about to experiment on.
So can you just state the last part of your question? You said, do we need to?
Is there a necessity to like pre-build the list of the stop list thing?
Okay, so two parts. The answer to this part is yes, the stop list has to be pre-built. Okay, and now say the second part of your question.
Or is it like once we get to know the documents that we are about to experiment on, then it's like dynamically created?
No, so the answer is yes to both. So it's not an either or like you had in your phrasing of the question. So the stop list has to be pre-constructed because otherwise you can't apply it.
Yeah.
And the stop list typically is, at least in part, dictated by the domain. So remember, I had this example that if you're trying to look at words, documents from the computer science department, the word computer is not very useful, so it should be on the stop list, right? Because almost every document in the computer science department will have the word computer in it. But if you're trying to separate papers from the computer science department and the biology department, the word computer becomes very important.
Yeah.
So in the first problem, the word computer should be in the stop list because it's not very important. In the second problem, the word computer must never be in the stop list, right?
Yeah.
So yes, the answer to your question is yes to both of them. Yes, you have to build it early, you have to pre-build the stop list, and yes, it has to take into account the domain specificity.
All right. Thank you.
Sure. Other questions? No other questions.
I'm just curious about if we're going to cover like different languages or like translations, or if we're mostly going to stick to like analyzing like the English language.
Translation meaning translation from one language to another?
Yes.
That is NLP. That is not the systems perspective of multimedia.
Okay.
Okay. So we will not talk about translations because that requires you to learn the grammar of languages. The techniques I'm going to teach you do not require knowing the grammar of a language and can be applied to any language. So Lauren, there was a fallacy in your question. Of course, we're going to focus on English. I only know, I guess, 6 languages, so I can't cover all languages anyway, 6 natural languages. But the techniques I'm going to teach you will be equally applicable to Sanskrit or Urdu or Chinese or Mandarin or Japanese or Russian or German, because they do not require the knowledge of the grammar. So that's actually another very interesting part of these techniques. So this term frequency table you can build if your document is in Russian. You're just tokenizing and you're just counting the frequency of particular tokens. You don't need to know what those words mean. So that's the very interesting part of it. So these techniques will work independent of language. However, there are problems such as automatic translation from one language to another, which have heated up now. I mean, when I was an undergrad, I knew of a master's student in my department who was doing automatic translation. I knew another master's student who was designing a program which will write stories automatically. There was a long time ago. These were classical AI problems. And then, because these problems were hard, they sort of became uninteresting. And more recently, there is again a big jump in interest in AI. And these problems have come back and have become very interesting again. So it's sort of, on a more relaxing note, it's sort of very interesting that when I finished my PhD in classical artificial intelligence, you could not get a job in AI. People thought AI is dead. It was totally useless. And now, if I'd finished my PhD now, oh my goodness, you guys won't believe the kind of salaries they're offering to people who have that sort of expertise. So science and technology and what is hot and what is not hot, it's like fashion. It goes up and down. But anyway, the point is the kind of things we are learning in this class, they actually were always in fashion, because these are things you always have to do. I don't say this simply because I'm teaching the class, but actually this is really true. The techniques I'm talking about have always been important and always been necessary, and actually are part also of AI work in this area. All right, so much so for history. Any other questions for today? All right, so since there are no other questions, we have only 1 minute left, guys. I actually would have wanted to have let you guys go a little earlier, because I know it's a lot more taxing to look at things on Zoom. So maybe next time we'll try maybe finish 10 minutes earlier, so that you guys can rest a little bit in case you have another class to take. But take a look at the class projects, and perhaps next lecture what I'll do is I'll very briefly go over the class projects. I'm trying to push you guys to make your selections so that you have enough time to work on them. And they would be very strongly correlated to a lot of the things you are learning in the lectures. So it's intended to be like that, okay? So with that, let me say goodbye to you guys. I'll see you guys next week. And you have the information about the TA's office hours and my office hours. So if any questions arise, please contact the TA first. If you can't resolve it, then please feel free to drop me an email, or actually come to the office hours so that we can actually talk. Sometimes talking is much more efficient to learn and understand things than in a bunch of long email exchanges, okay?